So just to explain a little bit why I am here, and then where I am coming from. Why I'm here is just because of the work that I'm doing there in Castres. So I'm, as you know now, so I'm a lecturer, so associate professor, we can say also. And then where am I? At the Université Paul Sabatier, who is based in Toulouse, but I'm not in Toulouse, I'm in Castres. So the most awkward situation that you can imagine. So Castres is just the delocalized center of the Toulouse University, and then I teach there for the chemistry department of the IUT. So for some of you, maybe you know what IUT is. So technological university institute, so more technology oriented, although it is at the university. It's not what we call BTS for those who know a little bit the French system. Then the research is done at LCC in a CNRS group, but the LCC is also based in Toulouse, but I don't do the research in Toulouse, I do all in Castres. So you will see also the strange situation makes that the group is very international in comparison to the other ones. So what I will explain today, I will try, to answer those questions. Can we, at the moment, we know that we have a problem at the moment on this planet, that the matter is limited, and then we use all in a more or less clever way. And then how could we do just to live a little bit longer in a normal way, and then I would say in a more convenient and comfortable life. And then can green chemistry, can catalysis help for that? I will try to give some answers. I'm not sure that we will have all of them. Not at all, but we will try to understand that just by questions. So I will start by something negative, this one, global warming. Our planet is burning. Maybe you know Midnight Oil, the Australian group. It was a good song in 1990. So it makes sure long time ago when they were speaking about the fire in the bush in Australia. When they were speaking about the birds that were burning. It's a little bit that you have to keep in mind. And then, yes, planet is at the moment eating up. Why? Just also by our use, but not only by our use. We use the fossil resources, we burn the fossil resources, we create CO2, CO2 goes in the atmosphere, we increase the temperature because of that. And then, in addition, we use also other things that make the CO2 increasing and then the temperature increasing. We deplete the ozone layer by using some CFC, so those carbofluorocarbons gases. Now we don't use them, we are supposed not to use them anymore, but all that is something that we need to think about. So one of the causes is the use of those fossil sources. So that is one problem. Could we maybe have a solution? Yes and no, I would say. Just for that, we could have a debate of 2 hours. Can we really diminish the temperature, diminish the CO2 of the planet just by using those type new resources? So the answer is yes and no, because to create those resources, we needed to use some industry, and especially for the photovoltaic cells. Silicon cells is not so simple to perform. We need a lot of energy for that, so we consume a lot of CO2 for it. Then after that, although it produces electricity, at the end we don't know how to recover, we don't know how to recycle. But in a certain time, in a certain duration of time, it's truth that we will produce less CO2 by the time that they will be in function. But to produce it, we need to be a bit dirty, I would say. The same with the wind system. The big magnets that we have at the big system are with those rare earth metals, so gadolinium especially, in those things, and then those oxides come from China in a way that is not very clean, I would say. So it's one of the solution, one of the problem, one of the solution. Another one that you know all, that the planet has a lot of resources, fossil resources. We use most of it. The easy one. So this is quite, I would say, quite old image, but it was just a quite image when we announced the end of the cheap oil. Cheap to get. Now, so we have, I think, normally more than 60, 80 years of oil at the moment in the resources, but they will be hard to remove, hard to take from the ground. So that's why we say the depletion, because there will be less, but also because it will be more expensive to get it. We already know it, but it's for other reasons, by neighbors. Then, maybe other sources, instead of taking those fossil ones that made millions of years to be formed, we could use the one that we have on the planet, I mean the green part. Those trees, we can transform those trees into resources. It exists already, but the question with that is, are you ready to harvest some places just for the production of chemical instead of production of food? That is a good question. You have 2 hours and then you can answer. Yeah? I mean, it's one of the questions that we have in mind. Is it that we really want? So should we find another solutions? I think there are, but that could be one also of the solutions. This one, you know it, and especially in Finland. And this is a circular economy. I mean, one of you know why I'm speaking about that. Actually, we are in this linear economy. You take, you make, you use, you waste. And then the waste, if you cannot do anything for that, you burn it. You burn it, you create CO2. Whoa. Bravo. And then the second one is you try, you make, you use, you try to recycle a part, then it goes to end at the end. This recycling economy is the one in which we start to be. I mean, in Finland, you are more in this that we can be in France at the moment. I mean, we have to be just honest in our economy. We know how it is in France. Then the best would be the one down. You see, in the one down, no waste. And that, if we succeed in that, is fantastic. But it's a scheme. Okay, that means that you can do that in some parts of the economy, but not everywhere. So you just take, you make, you use, you can recycle and make it again. Maybe not the same, but you can make something else. Or you can also use, reuse, return, use, reuse. So endless. That could be, for example, the bottle, the glass bottle that you recycle, in which you have this, how to say, this money that the fund in Germany, but I don't know how to say it in English. You know, when you have some money, I mean, you go, you have extra money that you give, that you pay for the bottle, and then when you go back and you give back the bottle, they give you money in addition.
Panti in Finnish.
Sorry?
Panti in Finnish.
Okay, so this. Deposit, thanks. Then, so that exists in Germany, for example. I mean, when I was living in Germany, the system was very efficient for that. In France, it was when I was like that, but it disappeared. And then that is something that we should do, for example, for the glass. I think that there is an economy in that we should continue. But we consume a lot of water in that. That has to be known. So also this use, reuse, repair, so sometimes, and then use, etc., etc. The circular economy is the best system that we, if we could use it, it would be the best that we could do, I would say. Let's speak about, that maybe might sound to some of you, this carbon cycle. Maybe you saw that maybe in college and lycée. Yeah. So that I took from a course that I give to the students, but it was just to show, in fact, what is important in the carbon economy. The carbon economy at the moment is when we look for the oil and gas, so I mean that, fossil fuels, you burn it, you extract, you burn it, it's CO2, it's here. The CO2 is recovered by the plant, and then normally you make the plant growing again by the photosynthesis. So still, the sun is still here and free, so let's take that as advantage. But in fact, by this, we can recover a little bit of CO2, but not all. And especially because we produce too much CO2 in comparison to what the plant can take, and especially because we cut a lot of plants. So some CO2 can be also in water, but I mean, normally it's quite a huge quantity that can be recovered by the oceans. In fact, I don't have the value in the head, but I know that it's quite a lot. But if you use something that is here, that you produce CO2, in fact, the cycle will be shorter, just because a tree I mean, a huge tree maybe will take some 50 years to be at the maximum of the size. Petroleum is 100,000 years, something like that. So not in our scale, it doesn't go. So we have to think that in terms of carbon cycle, and then all what we will do, all we will try to do, will be to try to find some short cycle or short carbon cycle economy. Then that is just for a stupid image that I found also. Is what when I mean, how many chemists are in the room? 1, 2, 3 then. The other one are not chemists at all. So the image of the chemistry that you have, it stinks, or you make perfume with that. Yeah. So if you see, it's something with a smell anyway. Then the image of chemistry is also the image of pollution. You know Bhopal, maybe the Bhopal catastrophe, but the pollution was done by a mistake of humans that we don't know how to store it. A chemical, I mean, as chemists we know, a chemical, if you store it conveniently, is no problem. Absolutely no problem. Then the mistake if there is a leak in the tankers, the oil tankers, and then you have the oil that is spilling. But it's not chemical contamination. It's just, I mean, it's not something that was done on purpose. AZF, no, maybe you don't know that because you are not from Toulouse. But so it was in 2001. No, I was not. I was in Germany at this time. So like,
2001.
yeah, 2001. And then in Toulouse we had a big explosion, the same as we have seen in Beirut some months ago. So this ammonium nitrate who exploded just by a small mistake, I would say. We will stay that way. But it makes a lot of gas, but nothing dangerous in terms of chemistry. But, I mean, not so, I would say, compared to what happened in Bhopal. In Bhopal, it was some compounds that were leaked from Union Carbide. They were doing normally the compounds for the batteries, if I'm not wrong. And then it went to the river with the consequences that we know. Seveso, maybe you know, or not. Italy. So it's a company where you have some chemicals that burned. They were just stored. They burned, but they were stored. Nothing more than that. So human mistakes by handling is not something that was done on purpose. No chemical is dangerous when it's closed. Once it's open, yeah. Then, so environmental problem can be seen when we think about chemistry. Earth problem also can be thought. And then that's why this, so for those who don't understand French, so it was for the Valentine's Day, and important is that we love each other. So just that, no matter. I mean, it was Plantu, I think he's dead, Plantu, no? He's dead recently. No, Plantu, il est pas mort? Si, je crois. So, but it was the only image that I found funny, that I use also for the courses. So now let's try to speak about some clean things, if we can. So you see some problems, some solutions that I try to propose. We might have some. We can even have a pause and starting to think and to debate together about some other solution. There are plenty. Chemists, we try to give some solution. We don't have the solution. There is no. That you don't know, you certainly know that. United Nations set some goals for the sustainable development. So no poverty, zero hunger. The zero hunger, the number 2 is also that. Do we have to grow plants to produce chemical that will favor the non-zero hunger? So it doesn't go. So if we use plants, we have to be clever. So good health, well-being, etc. Quality good education, that is so gender equality, clean water, that is something that is important, that will be an issue in some years. So clean energy, so we certainly, I don't know, here you have some nuclear plants, yeah? You have one that was built by French recently. But you know that decarbonation system or decarbonation energy, decarbonated energy, as our president say, Emmanuel. So this one. So he speaks about those decarbonation, and the decarbonation should be use of nuclear. We also have to think, is the nuclear so clean? I mean, in terms of energy produced, you produce only water. The only problem after is that you need to manage the waste. That is an issue. Then, so industry, innovation, etc., etc. That are some of the objectives. So this, I think, you could find it anywhere, even in English, even in Finnish, I think, on the web. So let's try to think about green chemistry, or clean chemistry, I would say. What have we done in France, in French, and then first for that? After Seveso, all the companies that produce a certain type of compound that are dangerous should have some security regulations inside. So, and then there are like this ISO something. I don't know if you know those quality system. Then there is some exigencies in terms of security. They need to do a lot of prevention. If you have a company in a place, all the surrounding must be aware about what is produced inside. If there is a problem, everyone around a certain periphery, I don't know exactly, but it's like 1-2 kilometers, must know how to evacuate the zone if there is a problem, or even the neighbors. I mean, not the one that are non-workers. I mean, just the neighbors. Then all the companies are visited, and then they control also the housing around, not to create so big buildings, and especially if you have an explosion. You know that the explosion normally doesn't do like this, it does like this. So you have a big building, I mean, you know that up you will take it.
What is SS?
Yeah, entreprise, companies in shortened way. Yeah. This entreprise. So it's yeah. So no, just a shortening. Sorry. Then REACH, you know that. I don't know if we reached it, but you know REACH. So it's evaluation from EU. It started in 2007, but I think that there is another regulation that has been updated. So registration, evaluation, and authorization of chemicals. So if you have some products that can be that can have some toxicological risks, as mutagenic, carcinogenics, or also problem on the reproduction, you need to show, and then to make all the paperwork to show that you have those products, and then you have to pay. The producer is the payer. The polluter is a payer, finally. So it's the only way that it is. But for that, you need to produce this compound more than 1 ton per year. So if you just stop just before, you don't need to. When we speak about green chemistry, and then or sustainable chemistry, or chimie durable, and then if you read it, I spoke in French of chimie soutenable, and I did on purpose, because it was just the country of insoutenable. So for those who can understand the French, maybe. And then those two persons, Anastase and Warner, wrote a text, wrote a concept, but it was not their own ideas. I mean, it's the idea of two people together, and then other scientists with them. And then they create some concept called green chemistry, but it's not the one that you hear on the TV. On the TV, green chemistry is just chemistry of plant. No, that is phytochemistry. So it's not something else. Green chemistry is not just that. I mean, green chemistry is chemistry. It's not something different than that. It's just the concept that we put inside is different. We will try to save things, save solvents, or use maybe less dangerous reagent, or trying to be more economy in atom. So I will explain that, maybe with games, I don't know if I can. So those two persons did it. So the definition is all the principles and the techniques to reduce or eliminate the use of or formation of nocive substances, so hazardous substances or toxic substances in conception, production, and use of chemical products. Find a solution to make it cleaner. find a solution to make it safer, find a solution to make it greener, I would say. And then you will say, yeah, but how can we know? There are some tools that can evaluate. It remains to be equations, but we will see that together. And then for that, we needed to define some principles, and then they define it 12. So here, I like it because it's quite easy to understand, I think. So you have all the all the topics that need to be studied. Prevent the waste. So if you make a reaction, for those who are not chemists, we will explain you how we chemists work. We have a big balloon, we put the product inside, reagent, solvent, and so on, we cook. And then after a certain time, the product is inside, but not only. And then it is not only the problem. So we remove the product with a lot of techniques. So we can precipitate, we can distillate, etc., etc. And then the rest, we need to throw. And then green chemistry is how can we do to throw the less as possible. So we need to find some methods in which we do not throw. We can recycle some part. I mean, solvent can be recycled, we can be distillated. Let's be honest, in the lab normally we don't do it. We put in the solvent place and then it is done in another company if they don't burn it. So that's why I was speaking about waste prevention, so preventing the waste by the reaction, then being econominaton. That means that to perform the reaction between two reagents, it will be, I take one, I take A, I take B, I just do the reunion of A and B, and it's not A with some tail, and then by doing the reaction, the tail is going out. No, it's just those two balls that are together, and then nothing more. The rest is nothing, normally. If we can be the more economic as possible. Then the synthesis have to be the less dangerous as possible. That is also something that chemists know. Sometimes we do a reaction, then we sweat quite a lot, even if we know how to handle. But you can use low temperature, specific protective gas, because you know that the compound can be sensitive and so on. If we can do the reaction without that, it would be better. If we can do the reaction without some reagents that we know to be dangerous, potentially explosive and so on, and then that are not so easy to handle, I would say, we will try to make this reaction easier. So we also try to conceive safer chemicals, trying to use solvent or I would say other products that are less polluting than the ones that are existing. For the solvent, just to remind, at the moment most of the solvents are oil-based, on petroleum. And then it's the petroleum that is taken, that we do the cracking, it's called. Yeah, cracking, hydrogenation, and then we distillate, and then we try to obtain some compounds with different boiling points. And then some of them are carcinogenic. So the benzene is carcinogenic, for example. But some are not so, I would say. The hexane is not top, but we should avoid it normally. And also we chemists are a bit crazy. We add some halogens sometimes because we found the properties are fantastic, but we have seen that now those compounds are dangerous and they should be avoided. And then we need to find other solution. At the moment, I mean, from years, the solution was to replace one solvent by another one. But it's just something like, I don't know how to say it in English, but I will say in French, is reculer pour mieux sauter. It's not exactly to take the right answer. I mean, the right answer should be to find better way. We will see how we can do. I mean, in our lab, what we decided not to change a solvent by another solvent is not to use solvent. It works for some reaction, not all of them. So we try to be energetically less gourmand, I don't know how to say that, demanding. We can try to use some renewable, but the renewable that we want to use should not be renewable coming from those, as I said, plants that were grown on purpose. I don't want that. I mean, my opinion is, if we do that, in fact, we lost already. Because there are some people that would like to eat instead of having those chemicals. So trying also to reduce the number of derivatives, so that is to explain that. I mean, the two chemicals that you have in front will know that if you need a medicine, so a drug sometimes can need more than 20, 30 steps. And then at each step, the yield, so the percentage of compound that you will get, can be very low. And then sometimes to get that, you need to protect one part so that you can work on another one. Then once you change the part you wanted, you can deprotect the other one, and then you can work on it. And that is one step and another step, and etc., etc. So patience is the first quality of a chemist. I mean, if you are not patient, don't do chemistry, I would say. Then catalysis, so I will speak about that a little bit in detail. Trying to conceive some product with in view how they will be degraded in the, for example, in the river, and then trying to see in real time how the compound is behaving to prevent the pollution. It's better to prevent than to cure. I mean, we cure what we did before. Now we try to prevent before. I mean, it's cheaper, and not only for the economy. I mean, for the population. Then trying to do some chemistry more reliable. So that we will see about. One thing is that you understand that we are not in a Care Bear world, so not Moominland, where everything is perfect. So if this concept of green chemistry is not economically viable, it will never be used, because the companies are there to make profits, and then if the profit is not, they will certainly not use it, except if there are some laws that obliges them. So we can speak about that after if you wish. But some companies know how to dig between the laws. So maybe you don't know him, Roger Sheldon. Nothing with Sheldon Cooper. Nothing, for those who know. But he's English. He worked all his life in Netherlands. He was first in a company, then he came at the university after. Then he tried to understand a little bit about those green chemistry. I will consider him as the pope of green chemistry, together with Anastasia and Warner, but he was more at the bench, I would say, compared to Anastasia and Warner. And then, I had a lot of discussion with him. He's a very, very interesting person. Then he showed with this E factor the mass of the waste on the mass of the product. The less the waste, better it is, you can imagine. Because in fact, in a chemical process, you need to, and especially in a company, the more you produce, even the waste, try to sell it. You don't have to burn it, you don't have to throw it. What is thrown, what is burnt, is lost. Burned maybe not, because you can gain energy, but what is thrown is thrown. And then that's why he showed that this huge industry of chemistry is the one that is the cleanest as possible. If you see, for example, the synthesis of ammonia. Ammonia is fantastic. Nitrogen, hydrogen, and then you do ammonia. So waste, considering just the equation, 0. It's not exactly 0. But you need to take the hydrogen from the methane. You will do a reaction for that. You need some catalyst. And then the nitrogen, you get it from air. It's easy. You burn the air, oxygen will turn into water, and then the nitrogen will not react, so you have gas that will be more clean, but you have some problem that you need to eliminate inside, so carbon monoxide and so on. But in terms of yield, it's fantastic for that. I mean, you don't throw mostly nothing. Fine chemistry is more complicated, and pharmaceutical chemistry is the worst. And then it is what I was saying, when you have to do a drug, you have a lot of reactions, a lot of steps, and then at each step you throw a lot. And then this throw that makes the E factor very, very high. So that is for the catalysis. You know maybe one of them. Which one do you know? Yeah. You know the is the first chemist we know. No, it's that is a joke that I will explain maybe, but later after the conference. Then the one on the right, you know him or not? I think it's Flamel. It's Nicolas Flamel. I think it's him. So it's the first alchemist, French one. So he was screwed, but he earned a lot of money saying that he could transform something into gold. In fact, it was not the case, but he earned a lot of money. And then he was living, for those who know Paris, he was living in Rue Quincampoix. And then if you go in this Rue Quincampoix, you have a place where is written, here was living Nicolas Flamel. So just one, if you go in Paris, go Rue Quincampoix, just on purpose, and then you will think about this day. So why I say that? Because in fact, the catalyst, the first one, they were here. And then especially in the reaction of panoramics, maybe the catalyst is not the salt that you put inside. It should be even the pot, because the pot is in copper. It could be, because you have some, let's say, distillation that were done and that were better when you do the distillation with copper, because the copper killed some compounds that were not good for the distillation. So just that. And then the poudre de perlimpinpin, for those who are not French, it's just like the magic dust that you put inside. But it's not magic. It's not a dust. But I mean, it's just that for the people who do not understand, it's something that we put inside that we can recover. There, here, you know that I'm coming from Paul Sabatier University. Here, Paul Sabatier, and it was a Nobel Prize of Chimie, so the I become a L, so I will correct it. So he got a stamp even in Sweden. So he created the catalysis as we know now. He started with powder, finely powder of, it was palladium, I think. He put that on tubes. And then he added gas together with hydrogen. And then he showed that if this powder was very fine, it was easy to transform the compound that were acetylene, I think, or ethylene, into alkane. So he could do the reaction that could be possible without, but with a higher energy. I mean, if it's not possible, if the reaction is not possible normally, the catalysis will not make it, the reaction working. Just the catalysis will make it faster. Maybe not cleaner, but faster. Then that is maybe to express a little bit. You have the reagent, you have the product down. So why is that? I mean, you can understand that if you fall down, you are more stable when you are down. It is what you see in a chemical reaction. You have some reagent. If they can react together, they will react in something more stable. Okay? But imagine that could be, if that could be spontaneous, I will give you just a short example. Ada and in Norway showed that it was possible to do nitric acid with a mixture of nitrogen, oxygen, and water. Nitrogen, oxygen, water. So air and water. He showed that we could do some nitric acid. For those who don't know, don't put nitric acid on the face. Otherwise, you know, Bob the Sponge, you will be like that. So, oops. Then, if we look, I mean, it was supposed not to ring. Luckily, we have that here. Is activation energy. Without the activation energy, our reaction could be react like this without doing anything. Activation energy is like a barrier you need to reach, and it is a reason why you need to put some temperature or any activation. It can be a hammer. Have you ever done aioli? You know what aioli is? Yeah. So you have a mortar. Mortar is one activation that we use in chemistry. It's called mechanochemistry. For example, so okay, it's more artisanal, this one. We have another method that we use at the moment. We use one at the moment in the lab with something else. So you imagine two glasses, more solid than glasses, closed with inside some small balls, and then it shakes with a very high speed, and then just by this we bring the energy that the reaction works without solvent. So it's not like in a kitchen where you have to cook with some liquid and so on. And then with a catalyst, in fact, this activation, this barrier that you need to reach, you can make it smaller. When it's smaller, it goes faster. You need less energy. So you can imagine also in terms of chemistry, in terms of industry, oh, okay, we need to heat less. And then you see the dollar on the eyes of the guy. Yeah. Then the catalyst, if we want to explain that, it could be that, I mean, the reaction is A and B are the reagent, the product is P, but P is the addition, the union of A and B. But the union is possible, but as I showed you, with a very high activation energy. When you have the catalyst, what happens, and especially here is heterogeneous, but it's not only, it can be also homogeneous that way. The catalyst will pick one reagent, will pick another one, will favor the meeting, they will react, and they will release. And then by this, so you heard it, it will react, and then it will release. So the catalyst is still there. So it can be reused, luckily. That is normally what should work in catalysis. It's not all the time like that. But what we try to do in catalysis, in our research, is to make some catalysts the more active as possible with the more cycle as possible. And then once you do the reaction, you can release the product. You can just add the system. We can have some other type clever system, some that we might to do together with Luc, using continuous flow. But we will speak about that at the end. So, for those who don't like chemistry, I'm sorry. Just one equation, very simple one. For those who do chemistry, we have done the first one, we all did it. Oxidation of alcohol with chromium is terrible. It works, but it's fully dirty. And then you can see that at the end you have this red, so chromium sulfate and then water. But here is the oxidation of one alcohol into a ketone. So I will not go into detail. The ketone has a nice smell. The alcohol has no smell, but the ketone is quite nice. And then, so by this, down is the catalytic version, just dioxygen and the alcohol, and then a catalyst. I didn't put it. The catalyst, I didn't put it because we can recover it. Here is other thing, it's homogeneous and heterogeneous. Yes, so what can we know about that? When you do the reaction, as I said, as in the kitchen, you have a big bowl, you have the chemicals inside, you put with a liquid, and then you boil, or you heat, I would say, and then the reaction will occur. And then, according to what you put inside, you can gain time. You can have those homogeneous or heterogeneous catalytical process. Homogeneous, the catalyst is dissolved in the sauce. Homogeneous, the catalyst is not dissolved, is in another phase. Should be solid but not dissolved into the reaction. So it's is those type of objects. For example, what you can see, those small white balls are porous compound like those, and then those reaction can help the system to be done. So the reaction is this one. Okay, so this one homogeneous with this aluminum chloride. This one is with that. Aluminum chloride is lost at the end of the reaction. Here is not, because it's recoverable. The advantage of the reaction, so you see, for example, in heterogeneous, we don't need solvent. We need solvent for homogeneous. We don't need water in the case of heterogeneous, but we need water in the other side because the aluminum complex needs to be separated. And then we don't need to recycle a solvent on the second step because there is no solvent. So you gain. And at the end, is that most impressive. Per kilogram of compound produced here is 4.5 kilos of aqueous effluent. It's huge for 1 kilo. You can imagine, I mean, the quantity is huge. On the other side is 35 grams. So that is not bad. So that I will, yes. You know decaffeinated coffee. You know we do it now or not? Because that is a process that we use for the decaffeinated coffee now. Or we did before. We use the coffee, we put that in with a solvent called dichloromethane. For those who know, they say, what? Yes, we washed the coffee with dichloromethane, a compound chlorinated, now forbidden in the chemical industry. And then the caffeine was dissolved in that. Then you add the coffee after. Then you dried it, then hoping that there is no more traces of dichloromethane. Yeah. I never liked the decaffeinated coffee. I prefer a real one. Yeah. And then this one is these supercritical fluids. So you have one gas, and that is something that you can answer. What happens if I put a gas into a high pressure? It will turn liquid. A gas, if you push it, it will become a liquid. And it's the case of CO2. CO2, you take it, in high pressure it becomes a liquid. If it becomes a liquid, it can be as a solvent. You use it as a solvent, you do the reaction you wish to do, and here you wash the coffee with the CO2. The caffeine goes with the CO2. Once it's done, you keep the coffee, you remove the CO2. The CO2 at this pressure is liquid, you open it, become a gas, and then even you can recover the caffeine. And then it was a way cleaner because it's only CO2, and then CO2 there is everywhere, but in fact when you do that, the CO2 is vanished. It's a way to make some reactions so that you use something that becomes a liquid at a certain pressure. You have the reaction at the end, you put again a normal atmospheric pressure, and then at this atmospheric pressure it's a gas, so it's very easy to remove. So some reaction that exists that can be done: oxidation, hydrogenation, esterification, and so on. So esterification, for example, is the one that we use with CO2. This esterification, we use it to make the biodiesel. Just so to explain, it's not only the same method, but this oleic acid and methanol is the biodiesel. That is some industrial compounds that have been existing, so you can understand maybe a little bit. Here up the system, you see the oxidant is only with N2O. N2O, you know it. I mean, the kids know because they use it now. Maybe not you. Don't use it. It's dangerous. But in some parties, they use those gas. And then, you know, this the gas, laughing gas. Yeah, it's dangerous.
Isn't that the one you use in the hospital?
Yeah, it is. But in hospital, it's okay. I mean, don't do it as a fun. I mean, so they use it. And then this gas, in fact, the advantage of that, once you remove the oxygen, it's only nitrogen. So that means 80% of the gas that we have in the room, we are not dead. So you see, so it's very simple. But it does the phenol, and then the phenol is huge. The one in the middle is a reaction very simple in which you have only H2O2, so hydroperoxide, eau oxygénée for the French ones. So the one you put in we put when we were younger, and then we were listening punk music, so to have the totally bleached hair. And then down is the oxygen to do some other reactions. That is also fatty acid. I was speaking about that. The fatty acid is also one of the resources that we need to use. We use it already for the biodiesel. So you know that. But the question is, do we need to use that instead of feeding the people? The debate is open. I think, I don't know, maybe if we use less, we would be less fat. So, I mean, in my case. You have also the coconut oil, for example. At the moment, we can have the big debate of that. Do we need to plant palm trees? Also, those palm trees. Do we need to plant that and then to kill the orangutan for Nutella? Just have a question on that. That is something with sugars and fats that we can use. So here I just pointed out some system. Carbohydrates are sugars. So sugar, when you do the fermentation, you have some alcohol, and then you have some glycerol also that you can obtain. Alcohol is distillated, then you have the ethanol you have in the cars. In the case of the vegetable, also you can do the transesterification. With the transesterification, you get some glycerol. We will see the glycerol later, but you have the biodiesel. You see, fuel, not from oil. I mean, a totally natural one. Then from glycerol, we can transform it into a process we create syngas. This process is funny. Funny, yeah. Historically, it's funny. It's called the Fischer-Tropsch synthesis. In fact, we need this mixture to do the Fischer-Tropsch synthesis. We can do methanol. Methanol is also used for the chemicals or for the biodiesel, but through the water gas shift, and then we can, all the Fischer-Tropsch synthesis, we can do these liquid hydrocarbons. I mean, all the fuel that you can have can be created from that. That was a technique, so Fischer-Tropsch, as you can hear, it sounds German. It was. And then they created that, I think it was at, I don't know if it was at the end of the First or at the beginning of the Second World War. It was at the beginning of the Second.
In between the two wars.
Yeah, in between.
1930.
Yeah. So when they needed oil, and then there was an embargo on the country. But they had a coal. You know why they invaded Lorraine? It's not for the climate. Huh? There was coal. For those who don't know Lorraine, go there. And then I live there, so yeah. But you left. No. So I mean, the climate is quite hard, I would say. But there was a lot of coal. There is no more, or not cheap one, I would say. And then, but the coal was used for that, and then they used the coal, and they transformed the coal into CO. The H2, they could obtain it through other type of reaction. I think it was using methane for H2, water gas shift reaction.
Yeah, but you can, what they were doing at the beginning, they use water.
Yeah, the water gas shift. The water gas shift.
Directly, yeah.
Yeah, and then with that they could obtain all the fuel that they wanted, and then they were for that independent to all the providers of fuel all around Europe, and then Middle East and some other origins, I would say. And this was stopped because they lost. You know that, I think. And then there was one country where they continued. Guess which one? You will see. It's very simple, and we will understand that. In terms of politics, which country got embargo of a lot of those countries around? No. Cuba, they had sugar. They could do rum. I mean, the car there could work with rum.
North Korea?
No. They could, but... no, at this time they were in peace.
Sudan?
No. Down.
South Africa.
South Africa. Because of the apartheid, they could not be delivered. I mean, they could not have some fuel. And then they kept the Fischer-Tropsch because they had a lot of coal. And then Sasol is not only oil, also is petroleum done by this way. And then they are, at the moment, I think they stopped it because they found some oil, but they have still the machine. I mean, if they need it, they can do it. In all over Europe, we don't use it anymore. Maybe we should think about that. Not with coal, with something else, but... So that was the Fischer-Tropsch process. So the two, they don't look happy, but okay. I didn't find better in their Wikipedia page. So you
Found a scientist at the beginning of the 20th century with a smile.
there was not.
It's impossible.
Yeah, there was not. And then you can see all they did. In fact, here you have that. And so if you need it, normally they will have the presentation. You can find it. I mean, that is quite interesting to find. That is interesting. The cost, the CO2 cost of the fuels for the planes. You know, I came by plane. I will not tell you the story because I was late in everything. So now I'm delayed for tomorrow. I mean, I will have to go through London. I wanted to go, but okay. So here you can see all the processes that are used to make those fuels, and then you can see that the fuel that is the cleanest is the Fischer-Tropsch synthesis. And then it's funny because it's, when you see the process, it looks ugly, dirty, but it's not so. Not the machine at the end. I mean, it's all rusted and then, but. So just, you can see. So for example, down, if you use the waste without plastic or only plastic, you see that better not to use the plastic because its cost of CO2 is huge. But if it is just the municipal waste without, you can find that it might be maybe normally the organic waste only. And then this one is maybe...
C'est quoi l'unité là?
Alors je sais pas. En haut c'est... En haut, c'est grammes de CO2 par mégajoule. Et alors le FT SPK, je sais pas ce que ça veut dire. J'ai oublié le A. Il faudrait que j'aille le chercher. Ah, c'est ça, Fischer-Tropsch synthesis paraphenic synthese. Voilà. C'est la synthèse Fischer-Tropsch en fonction de. Ouais, down, they did the Fischer-Tropsch using municipal solid waste, and then the unit is up. Yeah, the gram of CO2 expressed by megajoule. And then you see that if you want something cleaner, it's done that. But hydroprocessed ester and fatty acids, for example, you can find that in Sweden. Josef Samek does it from Stockholm University. I mean, he has a company who does that. He found something even more interesting recently. You can find it in Nature Communication. So just as a remark. Other type we can do also polymers with fatty acids. So the polymers, and then some of them you know, maybe some. So you can use a lot of those natural fat and oil. Oleic acid is what you can find in olive oil, but it will be stupid to use olive oil for that. Maybe the waste, but maybe the burnt one we could use. But at the moment we are using this burnt, I mean the used oil from cooking. You can upgrade it a little bit and you can use it as a fuel. Okay, it stinks a bit. You have the feeling that you are in a friteuse, but okay. Maybe. That is the glycerol that I was speaking before. Glycerol is quite interesting because you can transform a lot and then you can have a lot of application on it. Then I will just explain what we do. For the moment I did something very general. In Castres, so the small place in, as we say, is not the center of the world, it's just the end of the world. So we have some complexes with molybdenum, tungsten, and so we making complexes and we try to use those complexes to make some reaction cleaner. And then we try to use in solvent water if it is a solvent. In this case it's not, but no organic solvent if possible. We try to replace the petroleum using some substrates that are issued from biomass. I will explain that with some examples. And we try to graft the catalyst to recycle it. So the catalyst, normally, as I said, is like this magic dust. We graft it on a solid. It's not exactly heterogeneous catalysis because it's not grafted, it's ionically grafted. So it's like with a magnet. So I mean that it can react, but it will start again to be on the surface after. So very simple is that the reaction, the target reaction is that the model reaction we do. So it's a real molecule, it's called cyclooctene and then cyclooctene oxide, and then we try to do this reaction. What we try to do, and then I don't know if I have here, no I don't have that. We try to use it, that is what we do. That was before, you use a lot of compound that gives a lot of waste, or here, so some catalyst also, but we use in water. So water here is not a solvent, I will explain after. The catalysts that exist are here with a really high concentration. We try to have the maximum of the concentration at the minimum concentration of the other ones. And then the solvent, we don't have any. Then after you will see the student who participated in that, because the game was that. I mean, the student made the job. I mean, I started that, and then after I gave them, and I say, okay, try to improve it. And then the catalyst is up. It's very simple to do. I will not go into the detail. And then by this we can do, as you can see here, so the conversion, we can transform 74% of that. And then on what is transformed, 93% is this compound. We are quite efficient, but we could be better. But what the interesting is that the concentration of the catalyst is very low. So those two students were engineers from Brussels that came in. Then we can also calculate, that is something that I did. We can calculate how it works. So calculating is what? Is playing with a computer, just trying to imagine the molecules that are interacting and trying to see if it works the best. It can be discussed at infinite, but it's just an image. I mean, that is not maybe the complete answer. It's just one possible explanation that we have about the reactivity. We do some other experiments to try to understand how it works, but with the calculation we showed up, and then it's very similar to what exists in with the compound that is less clean, I would say. Then we played. So Thibaut and then Wiley also started to play. Chemistry is like Lego. I mean, the chemists will not say the contrary. We are kids, grown up, but we are kids. And then we try to play to remove an atom and then to replace an atom by another one and try to see how it works. And then we remove and we look. Does it work better? Yes, no. Why? So we are like kids. Et pourquoi? Et pourquoi? Et pourquoi? It's our work on each day. And then we try to understand why it works better. You see, if the ball is sulfur, it works better. The conversion is higher. Selectivity is more or less the same. But we can see with the calculation that, in fact, this energy d'activation, this activation energy is lower. Because it is lower, it's easier to react. So it is the reason why it is faster. I will go fast because I know that I can speak hours, so the students know that. Then we play the Lego also. We change whether the red, whether the green, whether both, whether known. So we played with that. So you can have one possible action. One is like it gives an electronic density to the molecule. The other one takes the electronic density, and then there is one who gives and the other one who takes. So it's like a push-pull system, we say. And then we have seen that if you have this one only, it works better. If you have this one, it works not good. And then if you put both, in fact, they are like canceling each other. So that was the game that we try to understand. I mean, we don't do only useful things. I mean, sometimes we try to do something, you say, what? Why? That is chemistry, that is research. So that is something that we do also a collaboration now 11 years old with Diana Pisk from Croatia. Then she came with complexes, and then we did a reaction with those complexes. We played a lot. We saw some activities. I mean, I will not go into detail, but then we transformed some products, and that was most of them were with collaborations. This one is with Morocco. We used a compound called imachalines, and then I say each time is a legal product that we took from Morocco, coming from a tree, the Atlas cedar tree. Then you have a big mixture that you can isolate, and then you can do the reaction that you see up. We showed that it was possible to do the same reaction, or mostly the same reaction, using cleaner conditions. This, no solvent. Here is chlorinated solvent. I mean, something toxic, I would say. Then we continued. We played our Lego game with limonene. Limonene, you know all. Have you been to a fish restaurant? Have you opened those paper that we gave you to clean the hands? Inside, in the paper, you have a lot of limonene. This smell of lemon. You know where it comes from? Yeah, from lemon, for sure. But from the peel. And then it is a waste of the orange juice industry. When they do the orange juice, you don't put the peel in. So you take the peel, then you remove this compound from the peel. It's quite cheap. It's a bit allergenic for some people, but okay. Nothing is perfect. But this limonene that you can see up, we can transform it, and then we can do it one pot. When I say one pot is all together, I mean I just put that, and that. I obtain this, I can follow, and then by the time I obtain those two. And those two, this one, I think it's this one, that is normally not possible to get directly except if you extract, you do a separation, and then you use a mercury compound. Mercury, no way. Okay, so here, one pot, and then you can get it. Not the highest yield, but you can get it. Then, yeah, Wiley and Yoon. So Wiley at this time was PhD. Robert Catava was Master 2. He got a PhD in Zagreb. And then Yoon was Master 2, did a PhD, and now he's in China, but he wants to come back. He misses us. So Finland, you. We also did some products with Ebo Academy. I mean, I was there this morning. And then Patrick Runeberg came with these Norlignans, so I don't even remember the name of the tree. Spruce, I think it is that they use. And then they can extract those lignans, and then in those lignans you can play with. So it's a bit complicated, but you start to have here to add the oxygen, and when you add the oxygen here, you have some reaction that make the cyclization. And then you can have the 5-member cycle or this compound. We found something more interesting recently with the similar reactivity. But we also showed here that we could obtain some compound like that. And then Slidin and Wiley tried also to graft the catalyst. That was not easy, so you can see that we have some idea. But for grafting the catalyst, it will be later with those. So POM, we say. So POM is nothing with apple to do. It's polyoxometalates. This compound, the first was described by a Swedish, Berzelius, maybe you know him. And then after the structure discovered by another Swedish, Kegin. But no, he was American, Kegin. No. So, and then, so what we do here, we do the catalysis with very low quantity. You can see 0.00002 is 2 ppm. So it's 2 molecules of catalyst for 1 million of compound that I want to transform. It's very low. I mean, at the moment, I don't know if you can see something so low, but we could do it. And then it was also Beatrice and then Daniel who did it. Just for information, Beatrice is now working for the French CSI. Just it's funny to see that. So that was the type of compound also that we did also with Jana. And then with Jana, we did some such compound, and we transformed not the cyclooctene, but we I didn't show it, but we transformed the cyclohexene into adipic acid. Adipic acid, you know it. Nylon, you know. You all wear some nylon things. The nylon come from that. And then we could find a method that was maybe at the moment not so efficient, but we started to go in this direction. And that what you see here, that are small nanoparticles of silica that we modified. And then we put at the periphery some pumps to do the reaction. Then I will not go into detail, but we can do with that, we can do a lot of oxidation. Then that is the idea that we wish that he knows. The dream of chemists. That means no workup. That means that you mix something and at the end you have what you get, and then that's it. And then, so it is what we wish to achieve. We will try to do something in this regards. So just to remember you that, you have seen that we were in linear economy, that step by step we try to go to this circular one by the use of the compounds. We tried in chemistry to help a little bit, maybe in the recycling first. In the circular we can, but we need to advance a little bit. So that is what we do, but it's not important for you. That are all the team for the people that you have seen in the work that I show. I mean, they were not, unfortunately, all together at the same time. Otherwise, it would have been complicated to manage, but okay. So you can see that there are a lot. I did that because there was a football championship at this time. And it was funny because, as you can see, there were Belgium, Croatian, for those who know the last one, the last championship. I mean, then that are the sponsors, so you can see. And then you are, because Institut Français is present. Yeah, because the first time that I came in Finland is by the help of the French Institute. I was I would say, laureat of the Sampo. And then I did a lot of some conferences at the university in 1 year. But not here. It was not here. It was on the big factory there. You remember? Yeah. And then, so the people who you can see the people who participate to the job. And then, just to thank all the members that we have at the moment. So it's funny because, as you can see, it's quite green around. So it's Castres. It's very small. It's not the case in Toulouse. I mean, not as green. And then, so he's French. She's Danish. She's French and Vietnamese. She's Croatian, Mexican, Lebanese. So very few French-speaking people. And then the two others, I mean, Pascal is my colleague. We work together. He never work alone, as you can see. And then myself. So just we all want to thank you for the presence, because in fact the work that you have seen is also their work. Without them, you would not see anything, or mostly anything, I would say, because the time devoted for the research is quite small and small each time. So thanks. And then if you have questions, I'm open to discussion.